So, what do you guys know about probabilities? Like, my little brother, so I always have to pick on my little brother. He said, "Jeff, are you teaching probabilities in that crazy ass class of yours?" I'm like, "Yes." He said, "Oh man, that's a bunch of shit, man. Either something's gonna happen or it ain't." And I'm like, "James, don't become a doctor, man. Don't, I don't want to go into surgery." I'm like, "What's my chances, doc?" 50-50? Oh, don't tell me this. I want to know the real odds, right? And if you tell me that it's a 50% chance it's going to snow today, here, that's crap. You agree with me? Do you agree with me?
Yeah.
Okay. So obviously, every probability can't be 50-50 because it's going to happen or it ain't. That's shit, right? The problem is people sometimes mistake very high probabilities for definitely going to happen and very low for definitely not, and then they get in trouble, right? For example, a really good example, and I don't care if you, all right, anyway, we'll see what happens with this. There is still a chance you'll get infected with COVID if you are vaccinated. You all know that, right? And yes, we're talking about COVID. Why the hell not? Right? There's a bunch of data with COVID that a bunch of people don't understand and have just gone on to say stupid things that have hurt people. So, the chances you're infected go down. You would. Now, if you're vaccinated and you get COVID, there's still a probability you can pass that on to somebody else. But the chances you will do that are incredibly lower if you're vaccinated. You guys still with me?
Yeah.
So people point, "I know somebody had a breakthrough case, that means the vaccine doesn't work." Oh, God, help me. So, if you yourself think COVID is a hoax or don't believe in vaccines, please keep it to yourself. My God, I don't need to hear that stupid shit. You're in college, this is good. There's a chance for you. There's a chance for you. All right, thank you. Okay. I love it. Now, so it goes beyond that, of course. If somebody said they went to Las Vegas and they hit the giant jackpot on a thing twice in a row, would you believe it? No. Does that mean it's impossible? Of course it's possible, right? It's just that it's really, really unlikely. If I flipped a coin 1,000 times, right? So two things. If I flipped a coin 1,000 times and I got 500 heads, right? Number one, I need to evaluate my life. I'm flipping a coin 1,000 times. Something's wrong. But number two, is that expected? Is that what you would expect? Flip a coin 1,000 times, get 500 heads? Is that, why? Why is it not expected?
Because 50-50 every time, so you get out more tails than heads one time, or more heads than tails.
All right. So I was ready for two kind of answers. Not quite that. I mean, that's correct. Which is why I would think that you would expect 500 heads out of 1,000 flips, right? No? Now, it would be weird to get exactly 500, but would it be weirder to get 3 heads from 1,000 flips? What would that be evidence of? If I flipped a coin 1,000 times, got 3 heads, what would that be evidence of?
Glitch in the matrix.
Glitch in the Matrix. We got the new Matrix coming out. The trailer just dropped. You should watch it. Looks pretty good. Holy shit. I'm sorry. I'm a little excited. I'm a little hopeful. All right. Enough of the Matrix. I appreciate that. But somebody else tell me, if you found a coin and you flipped it 1,000 times because you're really, really bored, and you only got 3 heads, what is that evidence for? What do you think is probably true about the coin? Is that something weird? Would that be unexpected? Yes. What does it mean about the coin, probably, then? You're all too nice. You would never be this devious, I guess. Could the coin be weighted?
Yeah.
Could somebody use that? Could that be somebody's coin they go to when they're going to flip it? So they could have weighted the coin so that the physics of it would make it flip and come to heads more often or less often, in this case. You guys kind of with me?
Yeah.
Sort of like messing with dice when you want to play craps or something? Same idea. Okay, so why is it not proof, just evidence? If I flip a coin 1,000 times, get 3 heads, why is it not proof that the coin was weighted? Why is it only evidence? I could do it again, sure. It would still just be evidence. I don't care if I do it 1 billion times. Because you can't, it's strong evidence, but of course it's not proof, because is it impossible to flip a normal coin 1,000 times and get 3 heads? Is that impossible? No, of course it is not impossible. Are you guys with me so far?
Yeah.
So a lot of the times probabilities are used in like court cases. You hear about DNA evidence, right? That has I can't remember, I gotta look it up, but it's like 99.something% chance, because there is a chance that there is a person with DNA similar enough to you that our testing methods consider you to be the same person, right? Our methods are not so good that we know exactly this is your DNA. We know we're like, this could be your DNA, right? But of course with other evidence that could together put you in jail, of course, right? Are you guys semi with me? A little bit? Okay, all right. Now, normally, if I have a lot of people in class, we do this thing called the birthday problem together, right? We could still try it, but are there a lot of people in class? No. You guys know about the birthday paradox, the birthday? So if I said, do you think that there's a high chance that somebody in a group of 45 people, that 2 people have the same birthday? What do you think? 45 people, 2 people with the same birthday. What do you think?
Possible.
It's a very good chance. I would put money on it happening. And the reason that we think it's not good is twofold. Either you think, nobody's got my birthday, so we think centric, we're like ourselves, we're like no one. Or you don't realize how many pairs of people. How many pairs of people are in this room? How many chances are there for there to be somebody with the same birthday? I compare you with you, you with you, you with you, you with you, you, and then I can do the whole thing again with you. You and you, you and you, and I'm not even over here yet, right? That's a lot of pairs of people. So when I think it's 34. I think if I get 34 in a room, it's 50% chance that you have 2 people with the same birthday. Once I get in the 40s, it's like 80% chance 2 people with the same birthday. It's crazy. So what does all this mean? Probabilities are not hardwired in our brains except for what we needed to survive, right? So for example, this is not a survival issue, but considering where we live, have you ever been in a place, looked at your watch and said, I might as well stay here for a couple hours, and then traffic's gonna let up? Have you ever been in this situation? Anybody? No?
Yes.
I've been in that. I'm like, we got a window. We got a window. Well, let's just sit down. I don't want to be in traffic. Let's just wait, right? So we'll go back to caveman days. We understood probability of this time of day. There's this thing, this tiger thing. There's a good chance that they're eating over here, so I'm going to go that way. Right? We understood probabilities to that point, but beyond that, we don't have a clue. We have no hardwiring of probability. That's why it seems counterintuitive very often. Here's a really good example. Anybody heard it? Let's make a deal.
Yeah.
Is it still?
I don't think it's there anymore.
No, I don't know, but it used to be there. And I'm thinking like back to the 70s or 80s or something. Holy shit! Back in the before times, in the way long time ago, the ancient history. There used to be somebody called Monty Hall that hosted the Let's Make It Up. At the end, stay with me now, stay with me. At the end of the show, they would take the people that won the most money in the regular part of the show, and they would say, you want to trade all the money in for a chance at picking a door, because behind one of these doors, let's say there's $50,000, right? And behind the other 2 doors, there are goats. So we're going to assume the people on the show aren't there to win a goat, right? They're not like, yes, I can get a goat, right? Getting a goat would be bad. So here's the idea. Somebody pick a door. 1, 2, 3.
3.
Okay, I heard 3. Okay. I open door 2, and I show you it's a goat. Okay, here comes spider goat. Spider goat. Spider goat. Does whatever spider goat. Okay. Do you want to switch doors? Would it make a difference probabilistically? Ooh, I like it. Probability-wise, would it make a difference if you stayed on the same door or switched? What do you guys think?
It's the same
No. It's not. You have a twice as good of a chance if you switch doors. Now let me see if I can make it make sense. All right. Let's say there are actually 100 doors. You with me? Let's say there's 100 doors. What are the chances? Somebody pick a number 1 to 100.
28.
You say 20? I heard 98 really good. I don't know. Let's say 98. All right, so the 98th door. All right, you picked the 98th door. That's what you picked. What's the probability that they picked the $50,000? Good. There's one door with the big prize out of 100 doors. Yes, that's the basic idea of probability. The number of things that match what I'm looking for divided by the total things that could happen. I got one shot at the big prize out of 100 possibilities. Yes? So what is the probability that that's the losing door? That's one of the losing doors. What's the probability we lose if we just stay with that door?
99.
Of course, it's the rest, yes. There's only two things that can happen, win or lose. If winning is 1 out of 100, losing is 99 out of 100. You have 99 out of 100 chances to lose. Let me stop for a minute. I want you guys with me. So are you feeling good that there's the money behind this door? Now, what do? I, as the host, who knows everything, because I'm the one who can see behind the damn doors, I open every door except number 2 and show you there's a goat behind all these doors. I don't open your door, of course. I open every other door, and I show you progressively more mutated goats. Should you switch doors? Why do you think? Now, if I open the door with the prize, isn't the show over? Isn't there no drama? Is that good for ratings? So either you just magically picked the right door, I don't think so, or I didn't open this one because it's got the freaking prize, right? Which one's more likely? The prize is here. In this case, there's a 99 times higher chance to win if you switch. In this case, there's a double chance. And the thing people don't take into account, you think there's 2 doors, it's 50-50, Jeff. No. It's 1/3, 2/3. So the minute I show you that's a goat, there's a 2/3 chance this door has the prize. Why did I pick this door? Either you picked the prize, 1/3 chance, or that one's got the prize and that's why I didn't open it, to keep the drama going. Yes, maybe. If you don't quite get this, it's okay. It's a really weird problem. I'm hoping the 100 one makes sense. Why did I not open him? Freaking prize is there. Holy shit. Okay, maybe? No? Has anyone ever seen the show Mythbusters? Or heard of it?
Yeah.
They did a whole show about this. They reconstructed the set. They actually did the practical experiment to show that it is a 2/3 chance. So the prize was here. You should have switched. You died. All right. Enough of that. So, again, that was not something you necessarily have to fully understand. It's just another situation where the probability is not intuitive. So I'm not trying to freak you out that, holy shit, chapter 3 is going to be impossible. But you've got to be careful about making quick assumptions about what it's going to be. Okay, and to me, it's one of the saddest things about the way the world is now, is not enough people understand probabilities, and you get taken by people who manipulate stuff when they talk to you, and they throw these probabilities up, and you don't know what they mean, and then they go down a YouTube rabbit hole, and it could even be in your family. Somebody could be living that experience. But anyway, all right. So, probability, the basic definition of probability. Probably not definition, like the basic way to calculate probability is what I should have said, but I'm not going to change it because I'm lazy. I already said this. The probability of some event is the number of things that match what we're looking for like when I said what's the probability we win, there's one door matching winning divided by the total number of things that could happen. Oh, that's a lot of words. Holy shit. This is the idea behind every probability problem. We are going to make some freaky looking probability formulas. The weird thing is, we're going to do a bunch of problems, get the answers before we know the formulas. We're going to create the formulas based on what the shit we did because it made sense. And then you're going to ask, well, why do I need the formula? And then I'm going to show you the problems where we need the formula. So there's a whole method here. Okay. All right, so everybody got this chicken scratch? Okay. No?
No.
What's up? Sorry.
I'm still writing it.
Oh, go ahead. Keep
No,
going.
it's me talking.
Oh, you? God, that was weird. I'm sorry, Audrey. You're looking at me like, what do you want from me?
Yeah.
I swear.
like what?
That was so weird.
I was like, I said yes.
It felt like it was coming right from you. Okay.
No. You've
Sorry.
done that so many times. Yeah,
All right.
every time that she talks, you think that I'm talking.
I know, it must be because of the acoustics of the wall or something. Or I got old ears. What do you want from me? Okay. So, for example, really, really simple example before we get anything too weird. Right, here's the really boring frickin' traditional probability problem, right? I put 4 red poker chips and 6 blue poker chips and 5 green poker chips, right? If I pick one poker chip, what's the probability that it's red?
Wait.
Uh-oh. So why is 1/3 not correct? What would be the most likely color to pick? Blue, because there's more of them. So obviously they can't all be 1/3 if there is a most likely one. What's the least likely thing to pick? Red. So it's got to be a smaller probability. If I had equal numbers of each, then it would have been 1/3. But we'll see why right now. Remember the basic idea. How many things match what I'm looking for? There's 4 reds, that 4 things match what I'm looking for, divided by 15. And what is that? No idea.
0.2667.
Sure, I like it. So we're going to round probabilities to 4 places. So that was almost like I planned to throw her over there, but I did not. And I believe it was Audrey that was saying that.
Yes.
Okay. All right. So let me give you a nice little problem that I love to give on quizzes and tests and stuff. Let's say that we talk to Grossmont students and Cuyamaca students. How do you spell Cuyamaca? I always have trouble with it. Cuyamaca, I messed something up. You know what I'm talking about. And I gotta apologize. Hey, Cuyamaca people, thanks. I'm sorry. C-U-Y-A. C-U-Y-A. Cuyamaca. There it is. Yeah. All right. It's like alphabet soup when they do it. All right. Now, let's say I talk to those people, and I ask them a question, and some say yes, some say no, some say me. Okay. So let's say that. So this is ripe for probability questions. All kinds of probability questions. What does this 9 mean? Just to make sure you can read this. What does that 9 mean? 9 people who are what? 9 gross amount people who said maybe. Good, right? How many Kuyamaka people said no?
1.
Ha ha ha. Sorry. How many Kuyamaka people said no? 21. All right, everybody can read this. I always make sure, because I always have somebody that's looking at it sideways or something. How many total people said yes? 18. Let's keep going. Let's see. 26 people said no. 10 people said maybe. What is that? 25. 49. So how many total people were there?
54.
Good. Not 108. Right? Don't add these people to these people, because these people are these people. Yes? Is that cool? You guys all see that? Okay, good. So it's only 54. You can double check this way. It better be 54 also. Let me stop for a minute. Let me know if anything's not clear, because it's one of my favorite prompts. So now I can ask you, see how I've got this set up? This is totally just set up for probably all kinds of probability questions. So I can ask you a real simple one, like, if I pick one person from this group, what's the probability I pick somebody who said no?
26 out of 54.
Good. The total number that match what I'm looking for. 26 people match what I'm looking for, yes? 26 people match what I'm looking for out of the total number of people it could have been. Let me stop for a minute. Did anyone, nobody's going to answer this as an affirmative, but somebody out there might have started to think 1 out of 26? Did it? You don't have to tell me if you did. If somebody wrote 1 out of 26, would you know what they were thinking? Because I see it all the time. Probably know they say 1 out of 26. All right, I love it. Maybe I shouldn't say any more about that. Nobody's going to make that mistake. But what they're thinking is they want one of these people. But that doesn't make any sense in terms of probabilities. Probability is all about how much relative amount of each thing is there. That's related to the probability. It could have been any of these 54 people. So out of those 54 people, 26 said no. That's the probability. That kicks ass.
So is the total number always going to be on the bottom unless...
I love it. The total number will always be the denominator unless I give you more information. So we're going to see that in a minute. If I told you something about the person, wouldn't it be less than, if I told you they said yes? Then it would be 18 total people I'm talking about, right? So we'll see that in a minute. Okay, what is this? Somebody help me.
148.
No. Oh, 0.48? That sounds...
Yeah.
0.48? 14. Okay, sorry. I thought the first number was a 1, and I'm like, there's no... Okay. And you can make that a percentage if you want to, right? 48.14%. So for these kind of problems, this is the work. This is the answer, right? If you only give me this, I'm going to take all the points off if you get it wrong. And I might take some points off for not showing work, right? I still have to wear I got this really, it's a little caustic. It's a red shirt with this really, show your work. It's a little bit much. So I should probably get a toned down version of that. But it's like, wow. All right, sorry. So what about, if I pick one person, what's probably, I pick a Kuyamaka student.
18 out of 54?
Nope.
29.
Yeah, how many are Kuyamaka students? 29. 18 would be if I said yes, right? Okay, good. You gotta be careful how to read this. So 29 out of 54, which is whatever the hell it is. 0.5376?
0.
70? taking your word for it. So is everybody else apparently. Maybe. Is that all right? Okay. Now, so those are pretty boring. Right? Those should be easy, hopefully. Just make sure you're looking at the right place. So let's get freaky. That didn't sound like so. So what about the probability that I pick somebody who said maybe, or they're a Grossmont student? So they said maybe, or they're from Grossmont. How many people match what I'm looking for now?
25.
How'd you get that?
Maybe it's 9 and gross money.
So maybe is,
40.
35?
26.
so I got, so, okay. Grossmont, 25, maybe 10,
35.
and that's still not quite right.
34.
Watch this. Watch this. If you count all these people, and you count all these people, who have you counted twice? You do 25 plus 10. Who have you counted twice? These. Don't just say maybes. You counted the Grossmont maybes twice. Yes? So I better subtract them off. They don't get 2 votes, do they? I really want that to make sense. So, or, well, so, let's put this up here. -9. What is the other way I could have done this problem? I could have just said 25 Grossmont people. How many maybes have I not counted yet? 1. So 26. 25 Grossmont people. 1 more maybe I haven't counted yet. Isn't that what this is? 25 plus 1? Of course, that we already did. Let me stop for a minute. I want to make sure everybody really understands why we had to subtract there. We didn't really have to subtract. We could have just been careful with how we counted. Just don't double count people, right? Okay. Let's do one more of those. What about, let me change my color system here. You guys see this? Ooh, that's nice.
Yeah.
It's been so long. Oh, dude, there's gonna be a little hit of that. I used to be able to get high all the time, now I can't spell it. Probability of no or Quimac. Here we go. Sounded, yeah. So you got the Quimacus, and then you can add the no's you haven't counted yet, right? Get 34. Or you can do Cuyamaca plus no, but then you better subtract these 21. Did you count 21 people twice if you did that? If I count all these people and all these people, I've counted those people twice. So either way you do it, you're going to end up with 34. So you can either do 29 plus 26 minus 21, or you could do 29 plus 5 no's I haven't counted yet. Those are both the same number. They're both 34. We haven't gotten that one yet. What's 34 out of 54? I have no idea. 0.6? 0.6296? Neat. You can make that into a percentage if you want to. All right. So what does OR seem to involve? It seems to involve adding and subtracting, right? What is that? Let me do this. Let's keep going. Oh yeah, you're good. What about and? Holy shit, Jeff. What about and? Probability is a Grossmont student. And they said yes. What does that mean? So what do they have to have done to be counted? Don't they have to do 2 things to be counted? Don't they have to be Grossmont student and they said yes? Isn't that more restrictive? Isn't that going to make the number smaller than it would normally be? How many people have done both of those things because it's an and? They have to have done both.
11.
Yes, and look at this. Another name for and is intersection. Do you see why we call it intersection? Because the intersection of Grossman and yes is 11. Out of what? No. Have I told you anything about the person? Nope. I said, what's the probability there, Grossman? And said yes. I don't know anything about this person. So who could it be? Any of the 54 people. So we still haven't seen an example where the bottom becomes different. Oh, shit. Especially if you're at home, you're not seeing much of this. Oh, yeah. So 11 out of 54, which is, I've heard tell that it's something. I have no idea what that is. 1/5, 0.2, so it's 0.2093. What is it? 2037? That's my one skill. All right. You're all like, try again, math boy. You were wrong in the third decimal place. That's not good enough. Fine. I'm sorry. Okay. So, where is this elusive, where the bottom changes? Here it is. What if I said, what's the probability that they said yes, given that they're a Cuyamaca student? The probability that they said yes, given they're from Cuyamaca. So what is it that tells me about the student? What do I know about them? That they're from Cuyamaca. Given they're from Cuyamaca. I really want that to make sense. This is the probability they said yes. So do I know they said yes? No, the freaking problem says the probability they said yes. I don't know. Given they're from Cuyamaca. So what's the bottom going to be now? How many people could it be? 29, good. And then you can just cover this shit. This is your whole universe here. Out of those 29 people, how many said yes? 7. Kick ass. That's the one time the bottom won't be the total, is if I give you information. Then it can throw people out. Then the bottom's going to get smaller. Have we talked about any formulas yet? No. You never do a formula if I give you everything you need to count. Yes? We are going to talk about the formulas, and then you're going to try to do the formulas on this kind of problem. You're going to make mistakes. And then I'm going to say the weirdest thing you've ever heard a math person say, don't use a formula, holy shit. Probabilities are based on counting. I only use formulas if I don't have stuff to count. And there will be problems where I won't give you everything to count. You'll have to use the formula. Okay, maybe? Maybe? Okay. So let's talk about some formulas we can develop from what we've done. So let's look at OR. Let's develop a formula for OR. Yeah, I'm going to work over there. Come here. Wee-haw! Focus. All right. So we're going to make a general formula for OR. So let's look at this problem here. What does this represent?
All of the Grossman students.
So this here, this ratio from the question. What does this represent? Grossman students, right? The probability of Grossman students, right? 25 out of 54, isn't that the probability of a Grossman student? So it looks like probability of A or B is the probability of A. So here, this is the probability of Grossman. Plus, what's this one? Probably maybe. So this is probability of one plus the probability of the other one minus, now what the hell is this?
The double counts.
Yes, be more specific.
The number of
9 who did what? 9 who were what?
Grossman students who
So they're gross month students, and they said maybe. So the probability of any or is the probability of one plus the probability of the other minus the probability of both. Which only makes sense. What's the only time you're going to subtract some? The ones that were both, because that's why they got double counted. So the only way you can get double counted is if you're in one section and the other one. If you're in both sections. Maybe no. So you guys look concerned. So again, isn't this probability of gross month 25 out of 54? Isn't this probably a maybe 10 out of 54? Isn't this probably a maybe and gross month 9 out of 54? So that's what we did without even knowing it. We really didn't do that. We counted, but based on what we did to count, we can create a formula. Every or will do this. Okay. Maybe. You guys love that shit. So real quick, something about or and. I haven't told you this though. Have I told you? No, I don't see a reason. Another concept talked about this. Let's say you're going to a club, and there is somebody at the door letting certain people in. Yes? Got a list and shit. So I come up to the door. I'm like, hey, I want to go to the club. I had a long week. I need some clubs. And they look at me. And I say, all right, if you want to get in the club, you gotta know Joe, the bartender. I'm like, I know Joe. Hey, Joe. And they say, and you gotta be rich. You can stop right there. And you gotta be dressed nice. You can, and then I just walk. I can't go in, can I? If it's an and bouncer, an and dude at the door, I ain't getting it because I gotta do all three. Yes. Now, what if I go the next day and there's the or bouncer? Right? He's got hair. The other guy was bald. He looks a little nicer. Right? I come up to him and I was like, "Hey, can I get in?" And he's like, "To get in, you gotta be rich." Oh shit. Or you gotta dress nice. Oh shit. Or you gotta know Joe. I know Joe, and I go in. So or is always gonna let more things in. So it's gonna be bigger. And is very restrictive. It's gotta meet all the requirements, so the answer is always gonna be smaller. That's why it makes sense that or is based in addition. It's adding more stuff in. It just doesn't want to over count, right? Maybe. Does that make any sense? I love that example. Okay, all right. So what about, and we're going to have to talk about on its own. And is a weird formula that we're going to have to kind of build, and the first step to build toward that is to talk about this. So how did we make this formula? What was 7?
Seven was the number of Keymock students that said yes.
So they were Cuyamaca students, and they said yes. So it looks like the top of this. Well, let's see if you guys are cool with this. All right. This is the answer here, right? And I guess we never made this into a decimal, but all right, stay with me. It's going to get a little weird. What's the probability of yes and Cuyamaca? It would be 7 out of the probability of yes and Cuyamaca. It would be 7 out of 54. If I said, what's the probability that I pick a student who's a Cuyamaca student and they said yes, do you know anything about the student? No, I didn't give you information. I didn't say given, right? Bottom's 54. Stay with me, stay with me. Does anyone disagree that mathematically this is the same thing? What would those 54s do mathematically? Wouldn't they cancel out? So math would look at me going, What? Sure, man, if you want to. It's the same thing. I don't give a shit. Sort of like adding zeros after decimal. Math is like, go for it. Have a great time. It's the same thing. Yes, yes. I love you guys. All right. Isn't this the probability of yes and Cuyamaca? 7 out of 54. Yes and Cuyamaca, 7 out of 54. Well, what's the 29 out of 54? Probability of Cuyamaca student, right? So here's one thing, here's another thing. The probability of A given B. And let me do one thing right now. Here's the symbol for given. It's a straight up and down line. That means given. Kinda sucks because some of you guys are going to think it's division. It is a straight up and down line and it means given. Why do math people have to make symbols? Because we're lazy as shit. Quicker to do that than write the word given. This formula is the probability of A and B divided by the probability of the given, the B in this case. Become a B. Yeah. That's what the given is. Holy shit. Let me throw something at you. I'm going to erase this stuff here. You ready? Go back to blue. Get away from blood red here. Where'd it go? Oh, has anyone ever seen? All right. We're not going to suddenly do a lot of this. I'm going to do one thing like this right now. Has anyone ever seen this kind of thing? Anyone know what that's called? Venn diagram. You guys ever seen that? Right. And again, just to remind you guys, you're not going to see any of this. You're not going to do homework with this. So why am I doing this? Just to show you one more way to think about this. So if I have the probability of A given B, what do I know has happened? What do I know is true? The probability of A given B. Which thing has happened? A and B are events. A could be the event being a Cuyamaca student. B could be the event saying yes. So if I say the probability of A given B, which thing has happened? Which thing do I know is true? A or B? I'll say it again. The probability of A given B. What has happened? What do I know is true? If I said the probability somebody smokes, given that their car smells like smoke, what do I know is true in that case?
Smells like smoke.
You're overthinking. I know their car smells like smoke. The probability that somebody smokes, given that their car smells like smoke, given this, that's the thing that has happened. That's the thing that I know. What's the probability he's the murderer, given that he had a motive? I know he had a motive. I'm given that he had a motive. Now the probability he's a murderer went up, yes? Okay, maybe. So the second thing is the thing I know happened, given this thing. So I know whatever the shit B means. B could mean had a motive. B could mean goes to Cuyamaca. B is just a general name for some event. So I know something here happened. What is the only way that A could also happen? Could this happen at the same time? Could that happen? If something here happened, could that happen at the same time? I want this to make sense. What's the only way something from A could happen? Where would it have to be? Could it be here to happen at the same time? No. It'd have to be in here, yes? What is this? Isn't this the part that is A and B? All right. So that's why it's the probability of A and B out of the probability of B. That's kind of a visualization of that formula. Okay. Let's do one more kind of problem focusing on this, and then we're going to call it an early day. Because I don't want to give myself an early day, and you guys get the fringe benefit of having it too. Okay. Anybody still copying this? Does anyone, well, shit. There's probably at least one person here that doesn't know cards too well. Anybody not know the cards? Like, do you not know what the suits are? Hearts, diamonds, spades, clubs, right? Do you know what, like, ace up to what? 1, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. Is that cool? Okay. All right, maybe I won't do a poker problem. Let me think. What's another good example? Oh.
Dice?
Say what?
Dice?
Dice, yeah, sort of. All right. All right, let's try this. You stay right there. All right, we're gonna try cards, just because. So there's ace, 2, 3, 9, 10, jack, queen, king, right? That's in each suit. So there's these cards of hearts, those cards of diamonds, those cards of clubs, those cards of spades. So there's 4 suits. There's hearts, diamonds, clubs, spades. I'm going to teach you guys how to count cards. No. No, we can't anymore. They've instituted all kinds of safeguards. We're too late to that party, guys. I'm sorry. They're not going to make another movie like 21. They've never seen the movie. The teacher that actually taught me. How do I get through these kids? All right. What's common with hearts and diamonds? What's the major feature of hearts and diamonds? They're both red. And clubs and spades are both black. Okay. So what's the probability? So how many total cards are there if there's 4 suits and there's 13 cards in each suit? 52. Okay. Having an older sibling, I know about 52 card pickup, where they just throw the deck in the air and say, pick them all up as fast as you can, I'm going to belch. Oh, this is fun. So happy. See, oh shit, I moved it over. Oh shit. Oh, there went the marker cap. There it is, right there. Okay. Yeah, I had a good life. Okay. I can steal this one. This is the dead marker. Okay.
If it's dead, why don't you just throw it in the trash?
I will. Okay. So it's 52 total ones. So let's start with a nice simple problem. If I pick one card, what's the probability I pick an 8? It's probably I pick an 8. So how do you think about it? Probability is the total number of things that match what I'm looking for, divided by the total number of things that could happen.
4 out of 50, or yeah, 4 out of 50.
Beautiful. There are 4 8s. There's 4 chances for me to get an 8 out of 52 total things that could happen. And what is that? That's, I'm not going to try to do it in my head. I feel like I should remember what that is. I do this often enough.
0.0769.
Okay, that sounds good. Now, What is the probability it's an 8? Given that it's a black card. Oh shit.
1 out of 52?
Nope. How many black 8s are there?
2 out of
2 black 8s, right? Right, there's an 8 of clubs, an 8 of spades. Then there's an 8 of diamonds, 8 of hearts, and those are red.
So there's
2 black 8s. But I know it's a black card, so how many cards am I talking about? 26. Now what's interesting about that, what is 2 divided by 26? 2 divided by 26. It's the same, yeah. Why does that make sense? Because I threw out half the deck and I threw out half the 8s. Didn't I throw out all the red cards? So I threw out all the red 8s. So it comes, okay, stay with me. Now let's see a couple more. What's the probability I pick a king? How many kings? 4. There's 4 of everything, right? There's 1 of each suit. And of course out of 52. It's the same damn thing, Jeff. All right. Don't worry, we're gonna get something different. 1 0 7 6. What is the probability it's a king given that it's a face card? All right, what the hell does that mean, Jeff? Well, how many cards have faces on them? Jack, queen, king. 12, right? There's 3 in each suit. There's 12 face cards. So what's the bottom gonna be? 12. Why? Given that it's a face card. So now it's out of 12. Out of those 12 face cards, how many are kings? Did we throw any kings out? When we focused on faces, don't they all have faces? So they're all 4 still there. So if somebody picks a card and they say it's black, all right, the probability of king doesn't change. It's still a 7.69% chance. But if they tell me, oh, it's a face card, the probability goes way the shit up to 33.33%, right? It's 4 out of 12, which is 1/3. Now they're become a number. Too many 3s. 3 is my nemesis. All right. Huh? It was you, of course. And that's going to happen the whole time. Let's just accept it.
No, I suggest you just put the line over it if it needs to be.
Oh yeah, sure. But we're going to round them to 4 places. Yeah. Okay. So this is going to lead into another idea known as conditional probabilities. The probability of a king. Would you say that it depends on if I know it's a face card or not? Does it change? Does the probability of a king change if I know that it's a face card? You can do it. What was it? 7.69. What does it become? 33.33, right? You can see it. The probability changes. So that's a special situation. We call that dependent. Doesn't the probability of king depend on if it's a face card or not? We see it happening. All right. So next time I'm going to have a worksheet, believe it or not. I'm going to have a practice quiz, believe it or not. Do you guys realize that on the homework sheet, did I put this up here? Let's take a look, Jeff. Let's all take a look. Yes, the only quiz that is on the homework sheet is the double quiz on chapter 3. So notice chapter 3 is not on test 2. So I sort of let chapter 3 stand alone. It's its own little thing. So that's what I'm going to have. This is the one quiz I'm going to give you a practice quiz for. All right, so that's what we'll do Tuesday. You guys go have a good weekend. Do what you can to make that happen. And I'll see y'all next week. Don't get used to getting out of here this early, by the way.